Okay, so what we want to talk about today is probability. We're going to talk about experimental and theoretical probability. What do you guys know about probability? Anything? Abby. Okay, it helps us to make predictions, absolutely. Okay, there's a chance of something happening, that is probability. Okay, so in your notes packet, on the first slide, you guys have, let me get there, this, okay? And there's a couple of vocab words we're going to fill in. Probability. A lot of time, probability is based off experiments, okay? So an experiment, probability is an experiment is an activity in which results are observed, okay? So we will be doing some experiments, we'll be doing some different things like that in which we're going to observe the results. Each observation is called a trial. Okay, so when we look at these different experiments and we maybe flip a coin, each flip of the coin is a trial, okay? Each result is called an outcome. So the result of an experiment is called an outcome. And then the sample space is the set of all possible outcomes of an experiment. Okay? So everything that could possibly happen. And we'll talk about that on the next slide. And then finally, the last one here, an event is a set of one or more outcomes. Okay? So if you look at the next slide, it kind of just gives you a blank chart. Okay? There's lots of different experiments we can do in terms of probability. Okay? The most common one is flipping a coin. Flipping a coin. That is an experiment. Okay, I flip the coin. I have a penny right here. I can flip the penny and I can do a trial and observe the outcome. The outcome was heads. Okay? The outcome was heads. The outcome was heads. Okay? So the sample space of flipping a coin are all the outcomes. What could possibly happen when I flip this coin? Ellie? You're going to get either heads or tails. Okay? An event, when I talk about events, that is specifically saying what is the chance of flipping heads. Okay? Heads is an event that happens. Tails could also be an event. Okay? Another experiment that we typically do with probability is rolling a number cube or some dice, a die, okay? The sample space, if I have a single die here, a dice, or a set of dice, what's the sample space just for one? What could happen? What are all the possible outcomes? Bracket. 1, 2, 3, 4, 5, or 6. Okay, that's our sample space. That's everything that could possibly happen. Now, an event, I could say, I want to find the probability of rolling a 5. A 5 would be one event. Does that make sense? Okay. There's lots of other experiments we could come up with. I could have a deck of cards. Okay. Picking a card from a deck of 52. There's 52 cards in the deck. Okay. I don't even want to list the whole sample space. Because the whole sample space is what? Is really a lot. There's 52 items, right? You have the ace of hearts, the ace of diamonds, the ace of clubs, the ace of spades. You have the 2 in each of those, the 3 in each of those, the 4 in each of those. So that's your entire sample space. All the possible outcomes are 52 possible outcomes, okay? The event might be, what's the probability that I get an ace of hearts? Or what's the probability I pick a hearts in general? Okay, so lots of different events that could happen there. Okay, does that make sense? Okay, now when we talk about probability, we talk about a range. Probability is a number from 0 to 100, or 0 to 1, 0% to 100%. Okay, it can be a fraction, a percent, or a decimal. It can be a fraction, decimal, or percent. Any of those. Sometimes we write it as a fraction, sometimes we write it as a decimal, sometimes as a percent. It tells you how likely an event is to happen. So if I say something has a 0% chance, that's down here. 0% is here. And 0% means that it is impossible. There are very few things in real life that I can talk about that are impossible, okay? Now, I would like to say there's a 0% chance that somebody's going to fail my class. But I know that's not true, right? Because somebody might. If they do nothing and they fail a lot of tests, they're going to fail my class, okay? So impossible might mean like there's a 0% chance that it's going to rain cats and dogs.
Yes, you never know. You never know.
No, it's not going to start raining cats and dogs, okay? That is impossible, okay? So if there's a 0% chance that I'm going to roll a 7 on a dice. It's only numbered 1 through 6. I can't get a 7, okay? So that's impossible. Now, all the way up to the other side, which is 100%, and this is certain. That means it's absolutely going to happen. Okay? There is a 100% chance. Nope, there's not a 100% chance that it will snow tomorrow. Okay? There is a 100% chance that the sun will rise. Yeah, it's going to happen. We may not see it, right? Because it might be cloudy, but the sun's still going to rise. It's still going to keep going. Now, I don't know, maybe someday the sun will burn out. I don't know. Not in our lifetime. Okay? So as of right now, there's a 100% chance the sun's going to come up tomorrow. Okay? Now, in between here, okay? In between here, in the middle, we have 50% or 1/2 or 0.5. Okay? And that would mean that we have a 50-50 chance. It might happen, it might not happen. Okay? If we're down here, we have a 25%, 0.25, or 1/4. And that would mean that it is unlikely. So anywhere down in this range, less than 50% is getting more and more unlikely that it will happen. Okay? I would like to say that it is unlikely that we will have an e-learning day this week. Unfortunately, based on the weather forecast, it might be likely that we have an e-learning day this week. And that's 75%, 0.75, or 3/4. Okay? Now, everything has to fall somewhere on that chart, right? What is the chance that Miss Helfring will give you homework tonight? 100%. It's on the board. You're going to have homework. Now, you might get it done in class, but you're going to have homework, okay? What is the chance that you're going to win the lottery?
Unlikely.
You guys?
Unlikely.
Impossible.
Oh yeah.
You guys can't.
Yeah.
No, you cannot. You're not old enough. You do not even have a chance to win the lottery because you must be 18 or older to play the lottery. The probability that I will win the lottery?
0.
Not 0.
Unlikely.
Very, 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 very unlikely. Okay, like as close as you can get to 0 without touching it. Okay, so there's a wide range. Okay, now the other blank here, the complement of an event is all the outcomes not in the event. So if I say the probability of us having an e-learning day is 75%, let's say it's up here at 75%, the complement is the opposite of that,
25.
not having an e-learning day, which is 25%. Okay? All right, so let's look at this slide. We're going to finish this slide before we go to lunch. Give the probability for each outcome. Now, if it's given as a percent, I'm going to leave it as a percent. So the probability of a team winning, 70%. The probability of a team losing, 30%. It would be the complement of that. Okay? The probability of spinning this spinner and getting a 1. Now, I'm going to write it as a fraction. There are 8 spots on the spinner, and 3 of them are 1s. So the probability of me spinning a 1 is 3/8. Okay, 3 out of 8. Because there are 3 possible ones and there's 8 total, so it's 3 out of 8. The probability of me spinning a 2, 3 out of 8, so 3/8. The probability of not a 3, 6/8, which is the same as 3/4. Does that make sense? Okay, let's go to lunch. We'll finish this after.
1, 2, 3, 1, 2. I just saw like a big number wheel, and I thought he was 1, 2, 3, 4, 5, 6, 7, 8. So yeah, I'm a genius. No, I'm not. You'll be young, probably.
Let's continue here. Okay, so looking at the next slide. Okay, there are a couple different kinds of probability we can talk about. We can talk about experimental probability or theoretical probability. So flip the page in your packet. Okay, experimental probability means you're comparing the number of trials or the number of times the event happens to the total number of trials. Okay, what experimental probability is really talking about is actually doing the experiment. Okay, you're actually doing it. So if I want to find the experimental probability of flipping heads on this coin, you can't just tell me it's 1 out of 2. Because I'd have to flip the coin and see what actually happens. Okay?
Heads.
I got tails.
Tails never fail.
I got tails.
Heads.
I got heads.
Ooh.
Whoops.
2 to 1.
Oh, floor.
It's 2 to 1.
Tails.
I got tails.
3 to 1. Tails.
And I got tails.
Let's go.
So the probability that I flip heads in this experiment was 1 out of 5. Okay, I flipped the coin 5 times. I got heads only 1 out of 5 times. So when we're looking at experimental probability, it's the number of times it actually happens to the total number of times you did it. So on this example, a marble is randomly drawn out of a bag and then replaced. The table shows the results after 50 draws. Estimate the probability of a red marble. So the probability gets written like this. Probability of red. How many times did red actually get drawn? 15 out of how many total? 50. We would simplify that. 15 out of 50 is 3 out of 10, right? Divide by 5, or 30%. Okay. The probability of drawing a green marble. Probability of green is what? 12 out of 50. We can simplify that to 24% if we want to write it as a percent or simplify the fraction. Okay? And then finally, letter C, the probability of yellow. The probability of yellow is 23 out of 50, which is 46%. Okay, and we could use a calculator to help us make those conversions. Does that make sense? Experimental probability.
Yep.
Okay. Now the opposite of experimental probability is theoretical probability. And theoretical probability is what should happen. Okay. So experimental is what actually happens when you do the experiment. Theoretical is, in theory, what should happen. If I take this penny and I flip it 10 times, how many times should I get heads? Eddie? 5, because the probability of getting heads is 1 out of 2, or 1/2. So it's the number of ways an event can occur compared to the total number of equally likely outcomes. The number of ways it can occur over the total. A coin, a number cube, or other object is called fair if all the outcomes are equally likely. Okay? This coin is a fair coin because it's just as likely as I get heads as tails. Okay? Now there are not fair coins. It would be a two-sided heads, right? Or two-sided tails. That would not be fair. Okay? So an experiment consists of rolling a fair number cube. Find the probability of each event. So if I have a die and I roll it, the probability of getting a 5, how many times can I get a 5? Or how many of the sides are a 5? 1 out of 6. You can just leave it as a fraction. So I have a 1 out of 6 chance of rolling a 5. The probability of an even number, 3 out of 6, because even numbers are 2, 4, and 6, so that's 3 out of a total of 6 sides, which would simplify to 1/2. Does that make sense? Okay. Now, if I were to roll 2 number cubes, okay, this is a chart of all of the possible outcomes in rolling 2 fair number cubes. So if I roll 2 cubes, I could roll a 1 and a 1. I could roll a 1 and a 2, a 1 and a 3, and so on, right? I could roll a 2 and a 1. A 1 and a 2 is different than a 2 and a 1, right? Because they're on different die, okay? So these are all of our possible outcomes. How many possible outcomes are there in rolling 2 number cubes? Oh, 36, okay? So there are 36 possible outcomes. Now, if I'm looking at the theoretical probability, what is the probability that the total shown equals 1? So if you'd add the 2 dice together, it would equal 1. What's the probability of that happening? How many of them? Lots of you are doing this. 0 out of 36, or 0%. It is impossible that the total of the 2 dice will equal 1. The lowest we can get is 2. Okay, the probability of having at least 1 6. Here's one with a 6. There's another one, there's another one, there's another one, there's another one. So we have to count how many have at least 1 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 36. I can't simplify it, I can just leave it just like that. Okay, of course if I wanted to divide and write it as a percent, I could, which would be 31%. Okay, questions there? Does that make sense? Okay, so then we can look at geometric probability. So find the probability that a point chosen randomly inside the circle is within the shaded region. Okay, remember when we did shaded regions? Like we found the area of the shaded part? That was geometry. Now we can tie that in with probability. I'm absolutely positive this is how they're going to use it on the MCA test. Okay, so they're going to say, what is the probability that if I were to throw a dart at that circle, that I'm going to land in the shaded part and not in the white part? So what we need, we're trying to find the probability of shaded, which means I need the shaded area over the total area. Okay, now I'll just grab my calculator out. You guys don't all need to. We need to find the total area first. What shape is this?
A circle.
A circle. So for total area, we need to find the area of that circle. How do you find the area of a circle? Mason.
It's the radius squared times pi.
Pi times radius squared. So 3.14 times 3 squared. 3.14 times 3 squared is 28.26. That's the number that's going to go on the bottom. To find the shaded part, I need the total minus the triangle. So 28.26 minus the triangle. How do I find the area of that triangle? Sydney.
Well, you do base times height and the base is 6 times 6 times 2.
Okay, 6 times 3 divided by 2. 6 times 3 divided by 2, that's 18 divided by 2 is 9. So 28.26 minus 9 is 19.26. So the shaded area is 19.26. Okay, we would not leave our answer like this in this case because you don't want decimals. We would divide, okay, 19.26 divided by 28.26 is 0.68 or 68% chance that you would land in the shaded region. Does that make sense to everyone?
Sure.
Okay, we're going to do one more activity, and it's going to result in you guys getting to eat some Skittles.
Yes.
Okay, so I need you to move up by Tucker. And send one person up here to grab a bag of Skittles. Do not open them. Do not open them.
I know, I thought about one of the most purple. So they all the same on Skittles?
One set of Skittles per table set. Okay, so do not set the Skittles aside for a second. Okay, so theoretically, okay, the Skittles factory produces, okay, in the factory they're producing the same number of red, orange, yellow, green, and purple Skittles in their factory each day. Okay, every day the same thing happens. They produce X amount of red, same amount of orange, yellow, green, and purple. Okay, in each pack of Skittles, okay, I bought these packs of Skittles, okay? No, stop. I said put this on the side for now. I don't want you doing anything with the bag of Skittles right now, okay? In each pack, there is said to be 15 Skittles, theoretically, okay? Now, we all know that that might not actually happen, okay? So, in theory, there are 15, okay? The Ziploc baggie in front of you contains 2 bags of these Skittles. How many Skittles should there be in the bag? Don't count them. Don't count them. There should be 30. Don't count them. Stop counting. I shouldn't have given you the bag of Skittles yet. Okay? Now, using the information above, I want to know theoretically how many of each color should there be. Okay? So if there's a total of 30, how many of those 30 should be red? 6, right? And there should be 6 orange, and there should be 6 yellow, and there should be 6 green, and there should be 6 purple. Theoretically. So the probability of red, 6 divided by 30, is 0.2 or 20%. 0.2 or 20%. Each one, in theory, should be the same. Agreed? If this factory makes the same amount of each color and they're putting them in the bags, theoretically we should have the same amount of every color in our bag. Now we know, in reality, that doesn't happen. Because I know that oftentimes I open up a bag of Skittles and I want them to be all red and they're not. I get more yellows and oranges and I'm super disappointed. Because yellow and orange is not my favorite. Okay? So now, what I want you to do, okay? Do not open the bag of Skittles. I don't want Skittles all over. Without taking the Skittles out of your Ziploc baggie, count how many are red, orange, yellow, green, and purple, and record that number in your table.
One, 2, 3, 4, 5, 6, 7 red or yellow. We should be able to sue them. We should sue them. 6 billion. 2, 3, 4, you know it. Just count how many purples there are. We don't even have any purples. We don't. Yeah. We've only got 28. What are purples? How many steps? I thought they were brown. These are not brown. Those are purple.
Okay. So record your numbers. In my bag of Skittles up here, here's what I had. I had 3 red, 7 orange, 8 yellow, 5 green, and 5 purple. Okay, that's what mine said. Now, I want you to find the probability of each of them. Use your calculator. Find the probability. In decimal form, to 2 decimal places, and then percentages.
Are we rounding to
2 decimal places. So you take how many there are divided by how many total will give you the decimal. Okay, so once you have the decimals, the percentages are really easy, right? Just scoot the decimal back too. 0.11 is 11%, 0.25 is 25%, and so on. Did anybody find any color that your experimental probability matched your theoretical probability? Which color? Aria? Orange, okay, yes.
Orange and yellow.
Orange and yellow. Ellie? Yellow?
Yellow.
Yellow?
Orange.
Orange?
Purple.
Purple?
Orange.
Orange?
Red.
Red? Okay, so some of us, it was close. Mine, I was close on a couple, but I definitely had more yellows than what I was supposed to have, right? And I had way less reds than what I was supposed to have, and that disappoints me because red is my favorite.
We got.
Okay, yes.
We got 12 reds.
You guys had all my reds.
We had 43%.
Okay, so now, if we look at all together, okay, if you look at the back side of your paper, on the back side, it says calculate the probability for the entire class. We're not going to do all the colors. I just want to know red, okay? So I'm going to do some adding. How many reds did you guys have? 6? 5? 4? Red? 4? 12? 6? 5? How many reds? 8? 9? 8. Okay, so in total, that's 79 reds between you. I should add mine. 79 plus 3, 82 reds. Okay, now we need total. How many of you had a total of 28 Skittles in your bag? If your group had 28 Skittles, raise your hand. 1, 2, 3, 4, 5, 6 groups. Raise your hand if your group had 29 Skittles. Nobody's groups had 29? Raise your hand if you had 27. 1, 2, 3, 4, 5, 6, 7 groups had 27. No, I don't think anybody had 30, did they? Did anybody? No, okay. So that's a total of 357 Skittles. Okay, now, if we find the probability now, it's 82 divided by 357. That is 0.23 or 23%. Are we getting closer to the theoretical probability? Mine, remember, with red, I started off at 11% red. Am I getting closer to the theoretical probability?
Yeah.
Absolutely. So the more experiments you do, the more Skittles we count, the closer we're going to get. Okay? Now, the Skittles are yours to split between the two of you. Okay? Your homework is on Delta Math.